This is Math 151, looking at topic G in the first unit, called the intermediate value theorem. Over the course of this semester, we'll study several famous theorems. Usually really famous and important theorems have some type of name. This one's called intermediate value theorem. And although generally speaking, formal proofs will not be part of this course, we are going to attempt to understand at least why the theorems make sense. Either informal logic or very often diagrams and graphs will help us to see this. So here's the statement of the intermediate value theorem. If f of x is continuous on the closed interval from a to b, and n is any value between f of a and f of b, then there is at least one number c. C is an element of the open interval from a to b, such that f of c equals n. Now, usually mathematicians, we like to pride ourselves on saying things as concisely as possible, using as few symbols as possible. And so often statements of theorems like this are very, very dense. And we need to unpack them in order to see what they really mean. So let's go ahead, and in this case, I am going to rely heavily on a diagram to help me figure out what this theorem is telling me. So I'm going to sketch here. I want to sketch a function f of x that's continuous on some closed interval from a to b. So let's just pick an a and a b. And it doesn't make any difference what I draw. I'm just going to kind of generically draw some function f of x with no jumps, no holes, no breaks, no asymptotes. It's got to be continuous. All right. N is a value between f of a and f of b. So f of a would be this y value right here. And f of b would be that y value right there. Pick n to be any value between f of b and f of a. So let's just say n is, here. The theorem then guarantees me that there's at least one number c between a and b, such that f of c is equal to n. Well, if you simply follow n over to the graph, we can see that indeed that y value corresponded to an x value between a and b, and that's that number c that's guaranteed to us by the intermediate value theorem. Now, we were just talking about continuity. Why is continuity such an important condition in this theorem? Well, if we didn't have a guarantee of a continuous graph, I couldn't claim that was true, because maybe that was a hole in the graph, or maybe there was a jump that excluded that value. So the continuity condition is a very important condition in this theorem. All right, a couple of conceptual questions, and then we'll look at just one example of how historically the knowledge of the intermediate value theorem may have been helpful. Here are the concept questions. First one, you fill a 6-inch tall glass with water. Was there ever a time when the height of the water in the glass was exactly 4.5 inches? Well, if I've got my glass of water, filling this cup is a continuous process, right? You're going to go through every possible height between 0 and 6 inches as you fill that. This is continuous. And so certainly at some point, there was exactly a height of 4.5 inches in this graph, in this glass of water. Now what about the next one? You build a 6-foot tall tower with blocks. Was there ever a time when the tower was exactly 4.5 feet tall? This time, we have to say that we're not guaranteed that result. It really depends on what size blocks we're using, right? If the blocks are half a foot each, then yeah, that would hit 4.5 feet. But if the blocks are a foot each, it wouldn't. So, building the tower with blocks is a discontinuous action, right? We don't go through every possible height. And so it's certainly possible that there was never a time when this tower was exactly 6 feet tall. In fact, just for simplicity, if I suppose that my blocks are 2 feet each, I would have gone from 2 to 4 to 6, for example. This is not specific, but... And it's certainly possible that we never hit that 4.5 feet because there was a discontinuity. We jumped from 2 to 4, and we jumped from 4 to 6. So not necessarily. And again, you can kind of see in an everyday life example why that requirement of continuity was so important. All right, here's a little bit more mathy example. Although currently we have fancy technology that easily helps us to find the zero of a function, just the x-intercept, right? Historically, without technology, that was a much more complex problem. Using the intermediate value theorem was actually a way to figure out, or at least to help us guide figuring out the zeros of a function. So I'm going to go ahead and we're going to pretend that we don't have graphing technology that just quickly and easily identifies a zero, although I am going to cheat and use a little technology to help me with the arithmetic. And I'm going to say, what if I wanted to rely on the concept of the intermediate value theorem to estimate the zero of that function correct to 3 decimal places? Do not use a graph on the calculator to help, so we won't graph it, but I am going to use a table because I don't want to have to plug all these numbers in by hand. So here's what we're going to do. I'm going to make myself a little table here of x values and f of x values. And since I would like to know when is this equal to 0, the first thing I need to do, if you think back to that intermediate value theorem again, is I need to find 2 points such that 0 is between the y values. So 0 is like my n here. And I'm looking for an f of a and an f of b. One has got to be smaller than 0, and one has got to be bigger than 0. Fortunately, that's fairly easy to do, because if I plug in x equals 0, 0 plus 0 minus 3, I get negative 3. And if I plug in x equals 1, 1 plus 3 is 4, 4 minus 3 is 1. So 0 is in between these y values. And so far, what I know is that the actual x value that I want is going to have to be somewhere between 0 and 1. So let's just pick a number between 0 and 1. Like 0.5, for example, might be convenient, right? The next thing I would do is plug 0.5 into this function and find the y value. Now, this is where I'm going to say, let's not go crazy. We do have some technology. So I just went ahead and put the function in here. And in my table, if I put in 0.5, I get a y value of negative 1.375. Now again, I'm going to notice between negative 1.375 and 1, 0 is in between. So I'm going to pick a new x value in between 0.5 and 1. Let's try 0.7. Okay. I'm just going to do the arithmetic off camera here, but I'm just plugging into my table again. And when I chose 0.7, I got negative 0.557. All right, notice 0 is no longer in between here, but 0 is between here and here. And so I'm going to pick a new x value between the 0.7 and the 1 to get closer. Let's try 0.8. Plugging that in, just using my calculator, I got negative 0.088. So I'm now between, or my 0 now lies between here and here. So I'm going to go between 0.8 and 1. Let's try 0.9. I got positive 0.429. The 0 is between here, so pick something between 0.8 and 0.9. I am going to try 0.85. I get 0.16413. Negative to positive, 0 is in between here and here, so let's go between 0.8 and 0.85. 0.82. Plugging that in gives me 0.01137. So between here and here is the 0, between 0.8 and 0.82. Let's try 0.81. Plugging that into my original function, again just using the calculator table, negative 0.0386. All right, 0 between here. So between 0.81 and 0.82. Let's try 0.815. That gave me negative 0.0137. So between here and here is the 0, between 0.815 and 0.82. Let's try 0.817. That gave me negative 0.0037. So 0 is between there and there, between 0.817 and 0.820. Let's try 0.818. .00134. So now I know I'm between these two, between 0.817 and 0.818. All right, we're getting closer to that 3 decimal places. So it just helps put the extra 0 on. So between those two numbers, let's try 0.8175. I get negative 0.0012. 0 is between those two numbers, so something between these two. How about 0.8177? That gave me negative 0.0002. So I'm between these two for my 0. Between these two, let's try 0.8178. I got positive 0.00034. So 0 is between those two numbers, meaning the x value is going to be between these two numbers. So the 0 of f of x satisfies 0.8177 is less than the actual x value, and 0.8178 is larger than the actual x value. Oops, I reversed my digits there. So it's between 0.8177 and 0.8178. Either way, this is going to round to 0.818 if I round correctly to 3 decimal places. So the actual zero of this function is about 0.818. Now, of course, we know that our graphing calculator can find that for us very, very quickly, but historically, without a graphing device like this would have been a way to guide that check for the zero. If I were to simply graph the function just to sort of help us see this, I could calculate the zero. And notice 0.8177 blah, blah, blah is the actual zero rounding off to 0.818. All right, so that brings us to the end of 1G.